Electricity consists of moving charges. Although electrons are normally the carriers of electricity, in this video we'll look at some situations where positive ions are also able to carry the charge. Salt happens to be a really poor conductor of electricity. In other words, it's an excellent insulator. I'm talking now about ordinary table salt, and if you could imagine that we take a crystal of solid salt and we cut it in a certain way, then we could have an equal number of sodium and chlorine atoms at the surface. But you can imagine that I could cut through that salt crystal a little bit differently. If I just happen to cut through it in a certain crystal direction or through a certain crystal plane, I might end up with some sodium atoms at the surface or perhaps many chlorine atoms at the surface. It would be very unlikely to break like that randomly, but it's clear that any crystal can be cut or cleaved along many different possible directions. And each might have a different surface structure. Of course, we know that as a whole, we have equal numbers of sodium and chlorine atoms, but at the surface, you might have a slight imbalance. Areas of the surface with different atoms present might have different local electrical properties because the outer electrons in a chlorine atom are more loosely bound orbits than outer electrons in sodium atoms. None of these electrons at the surface can move into the bulk of the crystal because it's an insulator. And you could think of it another way too. An electron in the interior of the crystal salt sees other electrons and atomic nuclei all over the place surrounding it. But an electron at the surface sees a completely different environment. It would have the entire bulk of the crystal below it, but free space above it. So all these electron orbits will be distorted at the surface of the material relative to the electron orbits around atoms inside a crystal. So it's natural that you might have a slight negative or positive surface charge even if there's no overall charge imbalance in an object. And that's the origin of static electricity in insulators in general. It's mainly a surface phenomenon. Salt is really interesting because it's a really good insulator. Pure distilled water is also a very good insulator, but when you dissolve salt in water, then we end up with something that's very highly conductive, and we'll look at this in a moment. Salt is a strong material due to its ionic bonds. Normally, things that are ionically bonded have really good, strong bonds. Chlorine is in group 7 on the periodic table, where it has one missing electron in its outer shell. And then sodium is in group 1 of the periodic table, so it has one electron in its outer shell. And that electron is not very tightly bound. So in sodium, it's very easy for it to give up that electron. Chlorine, however, would really like to have one electron in order to completely fill its outer shell. The atoms then lock together very nicely to make sodium chloride salt. But you see, now that we have the salt, now that we have a solid, the electrons are locked together pretty tightly. It's difficult to get any of the electrons to move around now, and that's why sodium chloride solid is not a very good conductor of electricity. Of course, there's still a lot of electrons in there. It's just that they're not mobile. They're not free to roam around the crystal like they would be in a metal, for example. Of course, anytime you have electrons, though, you can theoretically still get them to move if you have a strong enough force to push them around. Ionization refers to the process of separating an electron from its host atom. And this process is really difficult in solid sodium chloride, but it can be made easy. One hypothetical way that we might try to strip away an electron from one of the atoms and get it to move through the crystal would be to apply a voltage across a crystal of salt. An applied voltage is the really strong force from the point of view of an electron. If you try to do this, though, not much is going to happen in reality. You could imagine hooking up a battery to two electrodes, positive and negative, and start turning up the voltage on the battery. You're going to be able to reach an incredibly high voltage before you get the salt to become conductive. The electrons on the crystal are so tightly bound to their host atoms that it's difficult to attract them instead to the positive electrode or to repel them from the negative electrode. On the other hand, if you add some water to the salt and dissolve it, you actually end up with something that's a really good conductor. Here's how it works. You see, water is a polar molecule. The two hydrogen atoms are kind of grouped together on one side opposite the oxygen atom. So it makes one end of the water molecule a little bit more positive and one part of the molecule a little bit more negative. So it tends to get in between the sodium and chlorine ions. Since they're ionized, if we put a voltage across the solution, the ions are now free to move around. And in this case, it's not so much the individual electrons that are conducting the electricity, but rather the ions. This is the example that I was referring to at the beginning, where some of the charge carriers are positive. In this case, positive sodium ions travel towards the negative electrode. The chlorine ions, on the other hand, tend to drift towards the positive electrode. When they get to the electrode, electrons that have been injected from the battery meet the sodium ions and complete the circuit. Now at the positive electrode, each chlorine ion gives up its extra electron so that we have a kind of flow. And of course, these ions diffuse around inside the solution too. So once any chlorine ion is neutralized, it will spread around until it either finds a neutral sodium atom, which can give it back its extra electron, or it exits the solution as a gas. Of course, the chlorine atoms will bunch up a little bit near the positive electrode, and the sodium ions will bunch up a little bit near the positive electrode. This bunching of neutral atoms at the electrodes results in some current carrying limitations because the ion flow is then impeded. Let's now consider another situation. Imagine that you have no water at all, but instead you've just heated up the salt until it melts. It also makes a very good conductor of electricity for the same reason, because in a liquid, the atoms are kind of free to move around. That's what I've got illustrated on the next view graph. And it's very interesting because you could do an experiment like this, where you melt salt at 801 degrees Celsius. If you did it in a controlled environment where there's no oxygen or anything else that could interfere with your reaction, you could manufacture chlorine gas and sodium metal by starting off with salt. And here's how it works. Imagine that you have a battery and two electrodes and a tank of molten salt. The same thing's going to happen as before. The chlorine ions are going to be attracted to the positive electrode. Each chlorine ion will give up its extra electron and then immediately combine with another chlorine ion to create a single diatomic chlorine molecule. Chlorine is a gas. It's also a chemical weapon. It was used in World War I, and it's terrible. It reacts with nearly everything. Sodium is a metal, but it's also very highly reactive. So solid sodium pretty much just burns if there's any moisture or oxygen present. That's why you can't have a reaction like this in water. It has to be pure molten salt, not dissolved salt. When a sodium ion drifts over and meets an electron coming from the battery, you end up with solid sodium metal at the cathode or negative electrode. In practice, this reaction is actually very difficult to carry out because chlorine is so reactive that it just tends to degrade whatever anode material you use. Anytime you do electrolysis or electrochemistry, the anode or the positive electrode tends to be the electrode that degrades the most because you typically end up with something highly reactive. A lot of metals will just react with chlorine, just like sodium does, and form some other kind of salt by reacting with the anode itself. Once your anode starts getting coated with some kind of salt, it starts to become an insulator, and it prevents the current from flowing. So this causes a lot of complications when this sort of reaction is used industrially to produce gas, for example. If you try to carry out the same reaction in water-dissolved salt, it's a little bit more complicated. The same thing basically happens, and you end up with the sodium ions drifting towards the negative cathode and the chlorine ions drifting towards the positive anode. But because you have water in the mixture, you'll have some competition for the electrons on one side, and you have competition to receive electrons on the other. And it turns out that it's easier for the electrons to combine with the water than it is for them to combine with sodium. So you don't end up making very much sodium metal in this case. You end up electrolyzing water and producing hydrogen gas at the cathode. And at the anode, you might produce chlorine gas, oxygen gas, or some combination of the two. And in that situation, of course, you can see how the details of the reaction could become complicated because the ratio of chlorine that you're producing to oxygen that you're producing kind of depends on the concentration of reactants available at the electrode at that particular point in time. So in a solution of concentrated brine, you will typically produce more chlorine gas than oxygen gas. And if the brine is less concentrated, you would end up favoring the oxygen gas. However, if you have an anode material that happens to react easily with oxygen, you might still get more chlorine. We won't talk about it in too much more detail, but it's interesting because in all the reactions that I've just shown you, the battery is driving the current through some kind of chemical mixture, which results in chemical reactions taking place inside the mixture. But this process can also operate in reverse. You see, there are certain chemistries that will cause reactions to take place in solution, which then result in electrons flowing around the rest of the circuit. Of course, that's what happens in a battery. So if you understand the situation here, when the flow of electrons from a battery cause chemical reactions to occur in a solution, then you can very easily understand that the opposite might happen, that certain chemical reactions can cause electrons to flow around circuits. In this video, we've discussed how charges at surfaces can behave differently than charges in the bulk of a crystal. We discussed why ionic solids like salt are poor conductors of electricity, but when liquefied through melting or in solution, they become good conductors of electricity. In the next video, we'll take a closer look at the strength of the electric force which holds electrons in orbit around atoms, and we'll get a closer understanding of how crystals form.